Yeah, great. So, the talk will be about binary deprotection with Metasm. So first we'll introduce what is Metasm, and then we'll get into binary deprotection and maybe some other stuff. So, let's start. What is Metasm? Metasm is a framework. So it's a huge package of things that allows you to work with binary material. So you can debug a running program. You can disassemble a running program. You can running or not so running, in fact. You can compile stuff. You can create an executable that will run on Windows. You can create a shellcode from an assembler listing. You can do this kind of things. So it was written in Ruby. So Ruby is a scripting language. You may have heard about it. It's self-contained. It doesn't use some external binary for the assembling or things like that. So one of the main, the first features of the framework is an assembler and a disassembler. So right now it can handle IA32, so standard PC code. It can also handle MIPS code, so it runs. It can handle some embedded program. But the design of the framework is so that you can fairly easily add new architectures. So the feature set is quite complete on IA32. It can handle all the standard modes, the new 64 bits and stuff like that. So another feature is the debugger. So you can have a direct interface to the debugging primitives of many operating systems like Linux, Windows. It can also handle remote debugging through a network protocol used by GDB. So it's kind of a standard for this. Some of the newer features include a C compiler and a C decompiler, but we'll see that it's in the works. And you have a graphical user interface, so it's really easy. So a quick example of graphical interface. So this is a debugger that can handle Linux programs. And you have the brand new interface, which is graphical and handle pixels and colors and stuff. So we'll have a quick demo for this. Do we have a quick demo? Yeah, I think we have a quick demo. So yeah. So one of the features that is available in the framework is the ability to handle debugging over the network using the GDB protocol, and that's something that is exposed by you can enable when you run a virtual machine using VMware. You can enable a debugging stub that will allow you to interact with the virtual machine running. So we can. So I just launched. I launched a virtual machine running a Linux kernel, and now I'm going to connect to it using the GDB interface. And here we are. So now we have a wonderful guy that GUI that has just stopped the virtual machine from running, and we can now interact at the lowest level with the virtual machine state. So now we can have remote kernel debugging and stuff like that. You can single step, you can import symbols, you can have all kind of neat features. You can have backtraces that's useless here, but so it's just a quick demo to show that, well, it works. In fact, it didn't work, and I needed to fix bugs just before the presentation, but it will work in a few hours with the released version. So, okay, that's done. Get back to the slides. How does it work? So once again, the framework uses direct manipulation of the US primitives. That means we don't have an abstraction layer using an external program. We don't use hacks like reading the input and output of a GDB program or things like that. We directly interact with the operating system primitives, and that's very practical because that allows us to have a very fine and precise control on what's going on the machine. We can have all the possibilities offered by the operating system. So that's a low-level interface, and on top of that, Metasm offers a unified high-level interface that's the same for when you're working on a Linux program, on a Windows program, on a remote program using the GDB server protocol. And the high-level interface has what you would expect from a high-level debugger. You can set up conditional breakpoints. You can register actions to be run whenever some breakpoint is hit. You can have all kind of neat features, and it's really neat, easy to use, and it enables you to create very different kind of programs quite easily in a few lines of code, and those programs will run on Windows, on Linux, on a remote target. So we have samples that may dump, that may well. There are some samples in the framework that shows a few examples of what's possible to do. So one of the other features of Metasm is a C compiler. So for now, it's only a very simple C compiler. It generates some code that's quite ugly. It doesn't handle all the construct allowed by the C standard. It works for now only on x86 32 bits. But one key point is that it's integrated into the framework, and the framework is written in Ruby. So you can the goal of the framework is that you can take the working C compiler that can take a C source and output a Windows executable, and you can patch a small part that you may want to patch, and without having to worry about all the stuff that's around. So one of the things we've done with that is running a C source code and patching the framework so that the generated executable in the end is not a standard Windows binary, but it's a custom shellcode that will dynamically resolve symbols. That means that you can write a C source code that will that may run as an executable, and using the specially crafted linker, you may output the same functionality, but it will be embedded in a shellcode that will find all the library it needs, all the functions it needs dynamically at runtime. So this means that for shellcode development, it's a quite neat feature, because you can test your shellcode by outputting a real executable that you can double click and launch it, and then when the shellcode is done, you use the special linker, and you will generate a shellcode that will run on a remote machine in the address space of some other program, and it will do dynamic symbol resolution through the PEB and stuff like that. So that's one of the strengths of the framework, is that you have a set of features that works. I mean, here it's a C compiler, and you can reuse most of the features and change the single thing you want to change, and get some other working parts. Okay. So now to be more on topic of the talk here, we will talk about binary D protection. But we'll get more into this later. So the main part of this is we'll reuse one of the biggest features of Metasm, which is its disassembler. So you have a wonderful screenshot with lots of color and stuff, and it shows some program. I don't know what it does. Well, not here. So when you want to work with binary code using a disassembler, usually you'll get to IDA Pro. IDA Pro is a commercial decompiler, disassembler, and stuff like that. And it works very well on you compile a binary, you load it in IDA, and you get almost your source code directly. It's very good. It can recognize standard libraries. It can recognize standard functions. It handles symbols very well and stuff like that. But when you deal with protected code, you hit some very hard limitations of this software, because it's quite dumb. It does no code interpretation, and it has some strong hypotheses on the behavior of the binary code. So to see some of those hypotheses, we'll see that when IDA analyzes a program and finds a conditional jump, it will assume by default that both branches are taken. This may be a drawback when you have a code protection that have a conditional jump that is in fact not conditional, and you may have a fake condition so that the real code when run will always take one branch and never the other, and then the code protector will use this fact to make the other branch point to some junk code that will generate invalid code, and that will clutter the IDA output. You have also some other limitations, like in IDA, two binary instructions will never share the same memory space, and also that when IDA encounters a call instruction. Call is an assembly instruction that will run a subfunction and then normally get back to the caller. IDA assumes that the call will return, and many code obfuscators abuse this hypothesis and fool IDA. So we'll see an example of such protection. So here starts the item listing. We have some code, a call instruction, and then we have something that people familiar with assembly will find very strange. It's a OutSB instruction. It shouldn't be there. It just never happens in real code. And why do we see this in IDA? We see that the function that is called by the call instruction, sub40 stuff, it's not a real subfunction, but in fact it will patch its return address on the stack, so that's this add instruction. It will increment its return address, so that in fact when the code is run, you run through the instructions, you get into the call, the subfunction runs, and when the subfunction returns, you don't return back to the instruction here following the call, but 1 byte later through the TMP instruction. And there, IDA did not see that. So if the protection was a bit smarter, it could have put anything instead of the OutSB instruction, like a jump somewhere else, and then IDA would never have found the real code that is run by the processor. And so when you're trying to analyze the binary, you have to manually take care of this kind of stuff to find the real code that's interesting, because most of the time this will be the first instructions of the protected program, and what you're really interested in is after the call. So if the assembler can't follow it, you can do your analysis. So how does Metasm handle this kind of problem? The root of the problem in this case is that IDA does no analysis of the behavior of the code. Metasm, on the other hand, will try to emulate every instruction it encounters in the program to simulate the real behavior of the processor. So that's what we call binding. For an instruction, we associate the effects of the instruction. So a bit of a, well, for example, an add instruction, we see that, well, it's not really obvious, but you have the description of the semantic of the add instruction. You have the fact that the add instruction modifies its first argument using the addition of the first and the second argument, and you have also some effects on the flags of the processor that may be used later by conditional jumps or stuff like that. So we did this for most of the instructions in the IS32 opcode list. So we can have simple behavior like the add instruction, which just adds 2 registers. You can have more convoluted code like the call instruction. This one will push something on the stack. So you can use indirection, which is interact with memory. So for example, in the example before, the code, the binding of the call instruction will be that. That means when the call is run or emulated, it will behave like that. It will push this value on top of the stack and then decrement the stack pointer. Metasm also handles some special expressions like unknown, which means that some instructions have from a static point of view a random behavior. When you run rdtsc, you don't know after this instruction the value of EAX or EDX. So this can be expressed here, and when Metasm encounters this kind of instruction, if you have an addition after the rdtsc, like you increment EAX, there is special arithmetic applied to the unknown variable, so that unknown plus 1 is still unknown, and this kind of simplification. And so how do we use this binding to solve the problem that we encountered earlier with the call to a subfunction that modifies its return address? We use a symbolic emulation of the code flow. So this is what we call backtracking. So for example, that's just the code we've seen earlier. You have the call here, and then the content of the subfunction with the modification of the return address here on the second line with the add. So Metasm will run this code step by step. Well, it will not run it. It will emulate the code step by step. It will not assume that the call will ever return. So it considers the call as a jump. So it starts with the call, then it encounters the compare, add, test, and return. When it encounters the return instruction, the framework has all the information to know what the return instruction will do. And it knows that the return instruction will execute the code that is pointed by the top of the stack. So when it gets to ret, it will try to find what is the value at the top of the stack at this point in the program. So it will start backtracking top of the stack, starting at the ret instruction. Then the backtrace runs, so it will emulate each instruction one by one until it finds a numerical value that it can use as a result. So the first value is top of the stack, so draw the pointer ESP. Then you woke up, test does nothing, you woke up, add, so the add interacts with the top of the stack. It adds the value 1 to the original value that you searched. So it was searching for draw.ptr ESP, and now it searches for the value of ESP plus 1. Then you get to the call, so you still don't know what's the value of ESP plus 1. And then the call has the binding we saw earlier. It pushes an address on top of the stack. So now Metasm knows what is the value of draw.ptr ESP, and it has 1, and it has solved the backtrace. And so it will generate this output, which is you have some instructions, a call to a subfunction. It marks the call as no returning because it's not a standard call, and then the ret will jump back to the CMP. So in this case, you have directly the real code that is run by the processor. So what this means is that you can launch the deassembler on obfuscated code, and most of the time it will work around it will work its way around most of the obfuscation patterns. So it will find the real code you're interested in that may have been hidden by the fake call instruction. Okay, so now we've seen most interesting features of Metasm. We'll get into the analysis of the protection. So what's the step of so first, what is code protection? There are many people that want to hide the functioning of their code. So it may be I don't know, a shareware author that want to hide how it checks if the user registered this version. It may be a virus author that don't want antivirus people to know how the virus functions. It may be a ransomware that will hide your files, and it doesn't want you to find your files back until you pay the author or stuff like that. So how do you hide your code? So the first step, the simpler one, is compilation. So some people believe that you have your source code in C, you compile it, it's assembly is hard to read, so it's kind of protected. So it's a level of protection. If you want to go further, you can obfuscate code. That means instead of having a raw translation of your C code to assembly listing, you'll have another step, and then using your C listing, you'll obfuscate it and make it harder to read by people who know how to read assembly. So maybe instead of so the assembly listing is a series of very basic steps, and maybe at some point you want to add one to a register, and when using code obfuscation, instead of adding one to the register, you add two, and then you subtract one. So it's many simple steps that put together will make it very hard to read manually. When you read the listing, it's hard to get the meaning of the code. And then you have a step further, that's code virtualization. So this has nothing to do with VMware or stuff like that. In this context, code virtualization means that the real algorithm that the author wants to run is compiled to bytecode that is then interpreted by a virtual processor that is implemented in software. And the bytecode does not behave like standard assembly. So someone that's used to read x86 assembly will have difficulties to understand the bytecode. And then most of the time, when you virtualize code, you don't want to ease the task of the reversers, so you obfuscate your code virtualization. So how do we defeat this kind of protection? Here we'll concentrate on the best defense. So this will be the combination of code virtualization and obfuscation. So the key point is to work around the code virtualization. So the first step in this workaround is to understand the virtual machine architecture. How does it do addition? How does it manipulate memory? How does it manipulate its registers? And then that's when the obfuscation kick in, because the virtual machine is obfuscated. So you read the code that will make an addition on virtual registers, and this code is obfuscated and is hard to read. So first, you must defeat the code obfuscation. And then, ideally, the next step would be to generate a translator from the virtual bytecode to real assembly that you'll be able to analyze, and we'll see later maybe even to get back to C code or stuff like that. And so in this presentation, we'll introduce a framework to ease all of those steps. So what did we do earlier? We already worked in this field on the T2 challenge in 2007, and it was a really great reversing challenge, because you had all the protections we talked about. You had heavy code obfuscation, you had code virtualization with a quite clever code virtualization mechanism. And so what we did to solve this was that we added to the framework methods to handle obfuscation patterns. So first you had to run through the code manually. You see that sometimes instead of doing add register 1, it does add register 2, then sub register 1. So you added this pattern to a list of patterns, and then the framework would automatically find those patterns and replace it with the simpler form. And then you had a virtual processor generator, which is it was really interesting to do, but it's quite complicated. So you're invited to read the slides. It's on the Metasm website, and it's really interesting. So what we had is lovely error here. So we had this kind of things. No, where is it? It's here. Up. So we had this code to manipulate. So this is what's that? Okay. So this is this is not what it should be. Le code obfusqué du T2. Okay, so my teammate will rescue me. C'est le 2. C'est le 07 démo. 2. Yeah, okay, thank you. So we had to, when you the code that was run by the challenge looked like that. So okay, now it's done. So you had nothing like that, in fact. So it was a Windows driver that was loaded in the kernel, and it answered to the, well, it does stuff like that. So when you wanted to analyze the code, you obtain stuff like that. So it's really hard to read. You have lots of arithmetic manipulations. You have register rotated in every sense. You have all kind of stuff that's really hard to read. So what we did to solve this, you first had to read the assembly produced here. You can identify manually some patterns, like, I push a value, then I add something on the top of the stack, and then I pop a value. And so you can translate it to just a simple addition. And so you had a listing of of patterns. And so you added the list of patterns to the debugger, and as soon as the deassembler encountered a pattern, it will replace it with the simpler form, with the simplified form. So it was an unobfuscator, but you needed to manually read the code, find patterns, find the translation of the pattern, and create a list of things like that. And so finally you obtained code like this, which is much easier to read if you're familiar with assembly. So what we had earlier in the previous window is equivalent to, I think, 2 lines here. So the whole messy graph is now reduced to a few lines in this window. So it was quite powerful, but we needed to have a heavy manual intervention with reading the obfuscated code, finding patterns, finding how to solve the patterns and stuff like that. So the next step was to add automatic methods to deal with obfuscation. So the T2 was a reversing challenge, and then we had to work on a real commercial protector. So we reused some of the techniques we used on the T2 challenge, but more generalized. So that's what Alexandre will present to you.
Hi. So it works?
Yeah.
Okay. So the product we have studied is a real mainstream product that is used by millions in software, and sometimes it's also used, for example, on malwares. A big problem with protectors that use virtualization is that there exists actually no automatic tool to analyze this kind of protection. We know how to do some kind of automatic unpacking for classical packers from years now. Many solutions exist, for example, using instrumentalized virtual machine like VMware, or binary instrumentation like PIN from Intel. But there was no such kind of tool that exists for protectors that use virtualization. And one of the targets that one of the goals we want to tackle when doing this work was to propose a set of techniques that would allow some kind of automatic devirtualization, or to break virtualization automatically, whatever is the virtual machine that is used by the protector. So for the particular target we have studied, like I said, it's a real-world virtualization-based protection. Not the whole program is protected, but inside your program you can choose to protect some part, the most sensible that may contain a secret or a code you don't want anyone to know. The code actually is virtualized and compiled into virtual code, which is called bytecode, that is executed using the embedded interpreter, or which is also called the virtual machine. And something very particular to this protection is that each virtual machine that is generated by this protector is unique. So there's a kind of polymorphism, and we also see how we solve this problem. Code is massively obfuscated, so that's something we have already worked on, and we already had a few techniques. We developed some news. And also we can have the list of all the instruction handlers quite easily. Instruction handlers is a small piece of code that will emulate an opcode for the virtual machine. So, like Yoann said, we already had some kind of filtering processor. That means we're able to match pattern and destroy them really soon in the disassembly process, directly into the implementation of the processor in Metasm. We can easily walk through the control flow graph of a binary and manipulate this control flow on the fly. We can relink blocks together and do whatever we want. And we can also apply some kind of pattern when we walk through this graph. Trying patterns manually is very boring. That's not something we are interested in, and we try to automate this kind of job. So to sum up, what we wanted to do is to rewrite the code into a simpler form, but doing so, we want to preserve its semantics, of course, because we're interested by it. And as a side effect, we also would like to proceed to dead code elimination and to really get a simpler form. If we thought about that, one idea that quickly comes in mind is that compiler already do this kind of job. It's called basically optimizations. So we can do optimization with respect to different criteria, which may be speed, size, or anything else. Our own optimization criteria will be code conciseness, and because we want it to be easily analyzable with our classical tool. So the approach we proposed in this first part to break the obfuscation was to add an optimization module to our control flow graph also module. So for each of the handlers of the virtual machine, we will recover automatically its code and optimize it on the fly. So in order to do that, we have implemented few very classical optimization methods from compilers. For example, constant propagation. You can see that on the left you have the code that is not optimized, and on the right the code is optimized. You can see that on the first line, register AL is assigned with the value 12, and then we will propagate it to the third line when the same register is used. It's really some basic stuff that has been done in compiler for years, and we will use it to break obfuscation. Some other optimization techniques are, for example, constant folding. You may see that on the two-line CL register is assigned with this value, and then an operation is done just after. We will automatically solve this operation and assign, keep only one instruction, which is the segment of CL with the right value. Almost the same thing is operation folding. Here we will fold the first line and the three line into a single operation. So this is part of the techniques we have implemented into in our optimization modules. So right now I will show you a few examples of how it works on the protected code. First of all, I will show you what the protected code, obfuscated code looks like at the beginning. So this is the obfuscated code. You can see that there's lots of basic blocks that are linked together by jumps. This is a very classical in obfuscation. That's not a problem. We already have some techniques to merge all this code into a single basic blocks. But what we can see also is there's a lot of arithmetic operations. And our optimization method will be quite effective against this code. So remember the size of the whole code you have here. It may be something like 100 instructions. And once the optimization techniques are applied to this exactly same code, you will see that the code is quite more reduced. Yep. Okay, so now we have only five instructions because our optimization techniques have been applied, and we're now able to, if we want, manually analyze this code. Now it's quite easy. I will not have analyzed the first code. It will be too long and useless. But now we are able to do it, and also able to easily compute what is the semantic of its code. It will be the next part. So now that we have break the obfuscation of the virtual machine, we are able to analyze all its code, all its internals. So what we'll try to do is to break code virtualization. From a theoretical point of view, code virtualization is rather weak. Something like 13 years ago, someone proposed a theorem, and that says that if you know the interpreter, then you are able to code a compiler from your bytecode to native code, to sum up. And that's exactly what we do. But this theorem was only a proof of existence, and what we'll show you here is that actually we can do this. So I will use, to do this, we used functionality that Yoann has presented to you, which is binding, and we add a method to Metasm to automatically compute the binding of a block of code. It means we'll automatically compute the semantic of a block of code. You have here an example. It's the same handler that I will show you the optimization. And using the code binding method provided by Metasm, we are able to automatically compute its semantics. So the semantics is a set of symbolic expressions that encode all the effects of this basic block. So doing so, we will progressively build the whole description of the semantics of the interpreter. Actually, it's like if we rebuild the processor that is used by the virtual machine. So we totally automated these facts. When a new handler is encountered, it is automatically analyzed, optimized, and the result is put in a cache, and we load it on demand. Also, a very interesting point I will show you is that given the current program state and given the semantics we have computed, we are able to compute the next state of the virtual processor. It means we are able to automatically generate some kind of emulator for the virtual processor. And that's what we use to start from pure static analysis to an almost dynamic analysis. So if we took the handler's binding, I'll show you that have been automatically computed. Then we take the current context of the application. It's only a partial context here on the slide. So it's the context of the interpreter. And then we will inject this context into the binding. And then once the binding is solved, we have what we call the contextual binding. So it's all the effects of the operation on a concrete way. And with this, we're able to generate corresponding assembly to the effects of the binding. When I speak of generate assembly, it's native assembly. So we start from bytecode assembly, we analyze it and generate native assembly from it. And using this, we are quite easily able to compute context after execution of the current handler. It's what we call symbolic execution. And doing so, we are able to follow all the execution, all the bytecode execution flow, statically, simply using symbolic execution. And we had support for virtual calls and jump of the interpreters. And doing so, we're able to totally recover the whole chunk of code, of protected code within a native yet render assembly. So, demonstration. So okay, here we encountered a call to the virtual machine, and we have analyzed the context. So here's the context at the beginning of the execution, and we can execute one step, actually one instruction of the virtual machine. So the instruction handler is automatically disassembled and optimized. Binding is computed. Here is the context before execution of the binding. Then we inject binding into we inject the context into the binding, and after we solved it, and then we compute the context after the execution. It's a kind of automatically generated emulation of the virtual CPU, and then we generate a native yet render assembly. So we do this for all the handlers automatically. It will follow all the paths within the chunk of protected code, and at the end it will generate shell code, and we can have the whole chunk of protected code into a native assembly. So quite quickly we can see a few particularities into this code. There's lots of push and pop. All the values are pushed onto the stack before being used. So there's an aspect like a stack automaton. And also there's still a part of the obfuscation sometimes where it do useless instructions. And also we see lots of reference indirection using EDI registers. Actually, the virtual machine has its own context, and all the references that are made through EDI register will be referenced to its own context. One particularity of this protection, it used one-to-one mapping between native registers and virtual machine registers. So we'll exploit these fights to quickly recover a perfect native electronic code from the bytecode. So as I showed to you, the whole bytecode is compiled on the fly into a native assembly. There's still a part of obfuscation, and the aspect of stack automaton is quite annoying because it's quite hard to analyze it by hand. So we want to get rid of that. And what we do is that we'll reuse the optimization module onto this code, and we inject abstraction into the code to remove reference to the virtual machine context. When we know that our reference to EDI registers are reference to the virtual machine context, we can get rid of them, and thanks to the one-to-one mapping, we can recover native registers. To inject in abstraction, we simply extend the native EAT-Rondo CPU of Metasm, which is done quite easily in a few lines, and we will add the support for the virtual registers of the virtual CPU. So I will show you the same code once optimized and when we have injected abstractions into it. That's part of the debug log of the optimizations. So it's the exact same code as the one I showed you before, but once optimized, you can see that the whole code is once again reduced a lot, and we only used virtual registers that are register of the virtual machine that we can map directly to the native registers. So the code is now quite fine. We recover some kind of really clean code, and we will be able to reinject it automatically within the native applications. That will be the last steps of this current attack. We have, after applying optimization, injecting virtual registers, we'll then map back virtual register to native registers and compile the whole code and links it to the original unprotected applications. So I will show you it right now. So here you have few colors. The white block is the native unprotected code. The red one is the original code to the VM interpreter, but we have totally hooked that and replaced the bytecode by the native code we have generated. That's the one you have in yellow on the screen, and re-put it into the native application. So what we have done is that we have automatically removed all the virtualization from the application. So what we have done is to propose a set of techniques that would allow to automatically analyze virtualization-based protection and to automatically recover native code. All these techniques can be reused for many other implementations of code virtualization. They should be quite efficient. Optimization techniques are also quite effective against this kind of optimizations, obfuscation, sorry. They may be also strengthened by implementing other more effective techniques. What we have done is maybe called as partial evaluation or specialization. What we have done is a pre-computation of all the static elements because all the work we've done is purely a static analysis. We have never we have executed some code. So that's something maybe really interesting, for example, for automatic analysis tool like antivirus or some kind like this, some tool like that. We have pre-computed all the data transfer within the obfuscated code to optimize it. And we also have computed the application of the interpreter to the bytecode in order to be able to generate native Intel code. So this approach is really truly generic. And small drawback is that it requires relatively heavy computations. Most of the things we show in this presentation have been put in a cache and were not generated on the fly. But once you have your virtual processor, you can analyze with it all the virtual machines that use this same processor. So it's quite generic. The integration of the current deobfuscator is still its status is still as a prototype. It should be integrated later into the main framework as a kind of plugin. It's usable on x86 codes and some parts also cross-platform. Yoann will conclude on the compilation approach.
Yeah. So what we've seen here is that to analyze the protection, we started with disassembling the protected code, and we added hooks in the framework, so that when we recognize a jump into protected code, our methods will work and show to the user in the user interface only the unprotected code automatically as soon as it's encountered. But one of the things we use heavily is the deobfuscation module, and as Alexander has shown you, it uses very local and very simple techniques. It uses register manipulation within 2 or 3 instructions, but it wouldn't work very well on stuff obfuscated on a more global scale. If you added some jumps, or some other kind of block transition techniques, the obfuscation techniques we used would be defeated. So one of the other drawbacks of the current code is that it's specific to x86. And you can't reuse it on any other architecture, because add in IA32 is quite specific. So one of the leads we would like to pursue is working on a more abstract representation of the code, and this abstract representation would be C code. Why would that be? Well, for one, the architecture-specific code is quite reduced. You only need to have a few simple translation tables to go from specific assembly to C, which will be generic. Also, the C code is much more expressive than assembly, because in one C statement you can express stuff that would take tens of lines of assembly. You have a much better way to handle loops and generally conditional expressions. Like if you have an if test in C, it's just a statement, but in assembly it will be a specific instruction to compare some values, set up some flags, and then later another assembly instruction that will from the state of the flags determine if it should jump or not. So in this kind of thing, the C is much simpler to handle. So that's a great goal, but it has many limitations. For one, you first need to be able to generate C code from the assembly, and sometimes it's just hard to do with some specific assembly instructions, like rotation. You have no representation for that in C, so you must use multiple statements and indirect jumps and stuff like that. And also, when you read C code, you assume a certain set of properties on this code. Like when you manipulate C code, you manipulate functions, and a C function is assumed to return and have a generic ABI, so that it should preserve some registers and stuff like that. So this may be it may be quite hard to read in C, but we may work around it using attributes or stuff like that. So right now we have a small prototype of the compiler that I'll try to show you here. So we used a very simple example. So this is a small program that does some file manipulation. In fact, it's the program from the T2 challenge. But it's a very simple program, so we can see that it will manipulate things like, okay, full screen. Like it will create files. Well, it was easier to see that. Okay, so this code is quite simple. It's not obfuscated and nothing. It just calls a function. Test if the function fails or succeeds. If it succeeds, it continues, and if it fails, it will just bail with an error. And so this is the kind of code that we assume should be quite simple to decompile to C, and so that's what it's currently doing. So when it's done, okay, it's done. So we see here the result of the decompilation of this function. So it's C. So you get the function it calls. You have a call to an external function create file. Then it tests if the function succeeded, and if it succeeded, it continues. Otherwise, it just exits with an error. So we can see here that there are some of the attributes I talked earlier, like attribute. This is to allow the reverser to know that the decompiler has generated C code, but the C code is not generic C. It has some properties, like when you use the C variable EAX1. In fact, it's a representation of the EAX register at some point in the program. And so, using custom attributes, you can add more meaning to the C, and it's easier to get back to the original assembly using that. So right now it's quite a prototype for the decompiler, but when it works, it would allow us to use much more complex deobfuscation techniques, and to use optimization techniques on C is also much easier, because you have all the academic research in this domain. So it would be, I think it would be a great tool to deobfuscate obfuscated code. Okay, so that's it with the presentation. So, okay, if you have any question. Yeah.
What type of byte virtual machine that you use? What type of code virtualization that you use?
What type of?
What type of code virtualization?
Sorry, what?
What type of code virtualization?
Oh.
This one is the example showed by Alexander is Punk Buster, so it's yeah, so it's the protection used by Punk Buster, so it's used in commercial games and stuff like that.
You mean like Java sandbox in Linux, like that? The virtual machine?
Yes,
more or less like Java sandbox.
No, the virtual machine we talked about is a code obfuscation technique. It has nothing to do with like Java.
No, it's a kind of processor emulation. Small virtual processor emulation. Sorry?
No, it's a custom virtual machine that the code obfuscator wrote specially to make it hard to analyze. It doesn't reuse a QEMU or something like that. But yes, it's like QEMU, but it's a custom processor, so it's harder to analyze and understand the concepts behind it. Okay.
Excuse me. Where can we get sort of manual to read the assembly, like the manual?
In the framework, you have a README file, and you have many samples. You have many samples in the samples directory, so you can see how by examples how things are done. And on the blog we have a few posts where we explain, and we'll add more posts with which describe the internal of the framework.
Yeah. You guys going to build actual symbolic execution or monolith framework on top of the C stuff at some point, or is it?
Well, for now, the C stuff is more when you finally obtain a clean assembly, you may be able to decompile it, and then the meaning of the code will be obvious.
Okay, so that's purely for visualization, and all the symbolic execution analysis you do one layer down. Is that correct?
Yeah.
Yeah, that's what I.
So that's basically the plan for the future as well.
So
Yeah.
is it?
That's what we would like in the future. Yeah. Yeah.
So have you considered using an intermediate representation that's closer to an assembly language versus C? Because if you choose to extend it to other processors, it may be an incredible amount of work to write a decompile for every single processor.
Yeah, something we have